today I will discuss about the viscosity. Now, viscosity is the property of fluid. Now, what is the fluids? Fluids are the substances that cannot resist the external tangential stress applied on it, like liquids and gases are the fluids. Now, what is the viscosity? Viscosity is the property of fluids by virtue of which it opposes the relative motion between the layers of fluids. Now, these relative motions how to arise? Like we consider a solid surface and a liquid is flowing over these surfaces from this side to this side. If we divide this liquid into a large number of layers, at this layer in contact with the solid surface, the velocity is very low, assumed to be 0 at this layer. Velocity is very low, and with increasing height, the velocity of the layers of liquid increases. And this is how the relative motion arises between the liquid or fluid layers. But when the liquids or the gases, actually the fluids are in rest, there is no relative motion. So, there is no viscosity. So, viscosity arises when the fluids are in motion. Now, due to these relative motions between these two layers, if we consider these layers and these layers, between these two layers there arises an internal frictional force, and this force is called the viscous force, and in one word this internal friction is called the viscosity. So, viscosity is the property of fluid by virtue of which it opposes the relative motions between these layers. Okay. Now, types of fluid motions. There are two types of fluid motions. So, first one is steady or streamline motion. Streamline motion or flow, and second one is turbulent flow. Now, what is the steady or streamline flow? In this type of flow, the velocity at a given point inside the fluid, the magnitude and the directions of that velocity is constant throughout the time or with time. Like this, if we consider a tube and through this tube a fluid is flowing. This is the layers, and I consider 3 points, different 3 points A, B and C, and at this point velocity is V1, at this point velocity is V2, at this point velocity is V3, and these are the directions of velocity. As the velocity is the vector quantity, so velocity has magnitude as well as the direction. So, V1, V2 and V3 may be different, but V1 will remain constant throughout the time. V2 is also remain constant throughout the time and V3 will remain constant throughout the time. The magnitude and the directions of V1 and V2 and V3 will remain constant throughout the time. In this type of fluid, flow is called the steady or streamline flow. Now, the path, this path, the path followed by a particle in this type of motion or in this type of flow is called the streamline. So, this is a streamline. And for this type of flow or motion, the velocity should be very, very low, and the limiting velocity, what is the limiting velocity for this type of motion or flow, we will discuss later. Now, second one, the turbulent flow. Now, what is the turbulent flow? In this type of flow, this V1, V2 and V3, if we consider this fluid flowing through this tube, will not constant throughout the time. V1 is changing continuously, spontaneously, V2 is also changing and V3 will also changing. So, in this type of flow, that means turbulent flow, the velocity, the magnitude and the directions of velocity at a given point or at some given points will change continuously. That type of flow is called the turbulent flow. Now, I will discuss about a very important law in this regard, viscosity, the Newton's law of viscosity. Of viscosity. So, according this law, Newton's law of viscosity, according this law, the tangential stress of internal friction due to the relative motion between layers is proportional to the contact area of the contact and the velocity gradient. Now, what is the velocity gradient? So, according this law, according to this law, the tangential force of internal friction due to relative motion between two layers of fluid in streamline motion, is proportional to the area of contact of the layers of contact of the layers and the velocity gradient of them. Gradient of them. So, this is the Newton's law. Now, what is the velocity gradient? we consider a fluid is flow from this side to this side. This is x axis, this is z axis, and this is y axis in Cartesian coordinate. So, in this layer, and we divide this liquid into a large number of layers. And we know that with increasing height the velocity of these layers will increases. So, at a distance z from this axis x axis, this is z, we consider a layer AB, and above this axis we consider another layer CD whose distance is z plus dz. The distance of these layers AB is z, and distance of CD layer is z plus dz, and velocity of AB is v, and velocity of this layer is v plus dv. Now, we can say that the velocity gradient between these two layers is dv dz. So, velocity gradient is nothing but the change in velocity with respect to the change of the distance or height of the liquid. Now, according to Newton's law, if tangential force is F, if F is the tangential force, so according to Newton's law of viscosity, F is proportional to velocity gradient dv dz and also proportional to area of contact, where A is the area of contact of the layer and dv dz is the velocity gradient. So, F is equal to eta A dv dz, where eta is the proportionality constant in and known as the coefficient of viscosity. Known as the coefficient of viscosity. So, this is the Newton's law. Now, from this relation or equations, we can easily define eta. This is called eta, and this is known as the coefficient of viscosity. Now, definition of eta. Now, from these equations, F is equal to eta A dv dz if A is 1 and dv dz is 1, then eta is equal to F. Now, we can say that the coefficient of viscosity is nothing but the viscous force or tangential force of internal friction between two layers of unit area whose contact area is 1 and the velocity gradient between these two layers is 1. This is called the coefficient of viscosity. So, the coefficient of viscosity is the tangential force of internal friction due to relative motion between two layers when area of contact is 1 and velocity gradient is also 1. Gradient is also 1 or unity. So, this is the definition of coefficient of viscosity. Coefficient of viscosity depends of the liquids or fluids and temperature mainly, and it is also depends on pressure. Now, dimension of eta. Of eta. So, from these relations we can easily say that the Cesius unit of eta. So, Cesius unit of eta is gram centimeter inverse second inverse, and it is known as poise. And SI unit of eta is kg meter inverse second inverse, but the Cesius unit of coefficient of viscosity is most popular. There are two types of fluids, one is Newtonian fluids and another is non-Newtonian fluids. So, there are two types of fluids, one is Newtonian fluids and second one is non-Newtonian fluids. Now, what is the Newtonian fluids? Newtonian fluids are those whose coefficient of viscosity is constant at a given temperature and pressure. So, for this type of fluids, so for Newtonian fluids, fluids, the coefficient of viscosity eta is constant at a given temperature and pressure. Temperature and pressure. That means this type of fluids, Newtonian fluids, obey the Newton's law of viscosity, or Newton's law of viscosity holds good for this type of fluids. Now, example of this type of fluids are pure liquids like water, alcohol, etc., and the homogeneous solution. Now, what are the non-Newtonian fluids? Non-Newtonian fluids are those whose coefficient of viscosity is no longer constant at a given temperature and pressure, and it depends on the velocity gradient. So, for non-Newtonian fluids, the coefficient of viscosity is no longer constant at a given temperature and pressure. And it depends on the velocity gradient. We have already discussed about the velocity gradient. So, non-Newtonian fluids, coefficient of viscosity depends on the velocity gradient and is not the constant at a given pressure and temperature. Now, example of this type of fluids is non-homogeneous fluids like blood, glues, etc. Now, I will discuss about the critical velocity. The critical velocity, it is symbolized as Vc. V is the velocity and C stands for the critical. Earlier we have mentioned that for streamline flow, the velocity should not be very high or velocity should be low, but how low? This is the limiting velocity actually for the streamline flow. So, critical velocity is the limiting velocity at which the streamline motion turns into the turbulent motion. Experimentally, the scientist Reynolds showed this limiting velocity actually. So, experimentally showed that the critical velocity is the limiting velocity at which the streamline motion will become turbulent. So, this is the limiting velocity between the streamline motion and the turbulent motions, and it depends on the first the coefficient of viscosity of the fluids, the coefficient of viscosity of the fluid, the density of the fluid, density rho of the fluid, and third one is the diameter of the tube through which fluid flows. Diameter is d. So, critical velocity depends on the coefficient of viscosity, the density of the fluid, and the diameter of the tube through which fluid flows. But how it depends on the coefficient of viscosity, the density of the fluid, and the diameter of the tube? Now, I calculate that. So, Vc is proportional to, let us assume Vc is proportional to eta to the power alpha, the density rho to the power beta, and d, diameter of the tube, d to the power gamma. As we do not know the critical velocity depends on coefficient of viscosity, density of the fluid, and the diameter of the tube, how it depends on this type of quantity. So, using the dimensional method, we deduce, or we can easily calculate the value of alpha, beta, and gamma. So, if we omit this proportional sign, there is a constant, this is proportionality constant and known as the Reynolds number R. This is a dimensional less quantity, eta to the power alpha, rho to the power beta, and d to the power gamma, where R is proportionality constant and it is dimensionless. place. Now, using dimensional method, we can write dimension of Vc, that is dimension of velocity, that is L t to the power minus 1 is equal to, r is dimensionless. So, dimension of eta, we know that dimension of eta is m L inverse T inverse alpha, dimension of rho is m L to the power minus 3 to the power beta, and dimension of d is L, as d is the length. So, dimension of d is L. Now, m to the power alpha, plus m to the power beta. So, m to the power alpha plus beta, L to the power minus alpha minus 3 beta plus gamma, and t to the power minus alpha. Now, equating the power of m, L and t, we can write. So, power of m is right hand side to the power alpha plus beta and left hand side is 0. So, alpha plus beta is 0, this is equation number 1. Power of L is minus alpha minus 3 beta plus gamma is equal to 1, that is equation number 2, and minus alpha, power of t is minus alpha is equal to minus 1. So, alpha is equal to 1. Now, putting the value of alpha in equation number 1, we get 1 plus beta is 0. So, beta is equal to minus 1. Now, putting the value of alpha is equal to 1 and beta is equal to minus 1 in this equation, that is the equation number 2. So, from this equation minus 1 plus 3 plus gamma is 1. So, gamma is equals to 1 minus 2. So, minus 1. So, value of alpha is 1, value of beta is minus 1 and value of gamma is minus 1. So, Vc is equal to R eta to the power alpha. So, eta divided by rho d. So, this is the expression for critical velocity. So, critical velocity is directly proportional to the coefficient of viscosity and inversely proportional to the density of the fluid and the diameter of the tube through which it flows. And this quantity is known as the Reynolds number. It is a very important quantity in viscosity. So, it determines the motion, whether the motion will be turbulent or streamline. If the value of this R So, if the value of R is 0 to 2000, the motion will be streamlined or steady. When R is greater than 3000, it turbulent, and between 2000 to 3000 there is a transition period where the steady flow or streamlined motions will change to the turbulent motion. So, this is a very important quantity. Actually for water, this is very low viscous fluid, R is 1000, and for very high viscous it will increase up to 2000 for streamlined flow. Now, I will discuss flow of fluid through a narrow horizontal tube. That is Poiseuille's equations. So, Poiseuille showed that experimentally if a Newtonian fluid in streamlined motion flow through a narrow horizontal tube, that is capillary tube, then the volume of the liquid flowing out per second is proportional to the, so showed that for Newtonian fluid in streamlined motion, when it flows through a narrow horizontal tube, the volume flowing out per second, volume of the fluid flowing out per second is proportional directly to the fourth power So, if V is the volume of the liquid flowing out per second is proportional to the fourth power of the radius of the tube. And also directly proportional to the pressure difference between two ends of the tube, and inversely proportional to the coefficient of viscosity and length of the tube. So, this is the actually Poiseuille's equations. Poiseuille experimentally show that the volume flowing out per second is proportional to the pressure difference of the between two ends of the tube, fourth power of the radius of the tube, and inversely proportional to the length of the tube and coefficient of viscosity. Now, deduction of Poiseuille's equation. Equations. To deduce the Poiseuille's equations, here are some assumptions. First one is the fluid is Newtonian. Now we know the what is the Newtonian fluid, Newtonian. Second one is the motion is streamline, motion is streamline. Third one is there is no radial flow, there is no radial flow. And fourth one is the pressure difference between two ends is fully used up to overcome the viscosity. So, these are the assumptions. Now, we consider an incompressible fluid, that means liquid, flowing through a capillary tube of radius So, this is the capillary tube of length L and radius A. This is the axis of the capillary tube. So, let us consider an incompressible fluid, that means liquid is flowing through this capillary tube, and the pressure of this end is P1 and this end is P2, and P1 is greater than P2, and P is the constant pressure difference between two ends. P is equal to P1 minus P2. Now, the velocity along this axis is maximum, and if we goes from this side to this side and from this side to this side, the velocity will decreases and reach to 0 at the wall of this tube at this side. So, velocity profile is like that, maximum velocity along this axis and Now we consider from this axis at a distance r, the velocity of this layer is v, and velocity gradient between these two layers, the distance from this axis is r and r plus dr. This layer is r plus dr and velocity is v plus dv. So, velocity gradient between these two layers is dv dr. So, the tangential or viscous force F1 is equal to 2 pi r eta L dv dr. And the force due to the tangential force F1 is equal to 2 pi r eta L dv dr, and force due to the pressure difference P is F2 is equal to pi r square into P. As we know that pressure is equal to force per unit area. So, at steady state F1 is equal to F2. So, 2 pi r eta L dv dr is equal to pi r square into P. So, from these equations dv dr is equal to Pr divided by 2 eta L. Now, dv is equal to Pr by 2 eta L dr. So, 0 to v, if the limit of velocity is 0 to v, then limit of r is a to r So, V is equal to P by 2 eta L, 4 eta L r square minus a square. So, this is the velocity profile and this is the equation of parabola. Now, V at axis is equal to P by 4 eta L at axis, R is 0, at axis R is 0. So, P a square by 4 eta L, and this is the maximum velocity. Now, let us consider dV is the volume of fluid, liquid flowing out per second through the cylindrical shell of radii R and R plus dr. So, dV is equals to 2 pi r dr into V. So, V is the velocity. So, now putting the value of V in this equation, dr P by 4 eta L r square minus a square. So, total volume of the liquid flowing out per second through the tube is V. Two pi P by 4 eta L r cube minus a square r dr, and the limit of r is 0 to a. Now, integrating this, 2 pi P 4 eta L r to the power 4 by 4 minus a square r square by 2, 0 to a. So, 2 pi P 4 eta L a to the power 4 by 4 minus a to the power 4 by 2, putting the limit. So, pi P by 2 eta L a to the power 4 by 4. So, pi P a to the power 4 by 8 eta L. So, this is the expression for volume of the liquid flowing through the capillary tube per unit time or per second. So, eta is equal to pi P a to the power 4 8 V L. So, this is the Poiseuille's equation, and using these equations we can easily derive the coefficient of viscosity, knowing the radius of the capillary tube, pressure difference between two ends and length of the capillary tube, and measure the volume flowing out per second.